Hello, everybody. My name is Brent Paltala. I am the Executive Director of Partners in Research Canada, and I will be your host today for this Junior Astronaut webinar featuring Philip Reger from Western University. I'll give Philip an opportunity to introduce himself before we get going. So with no further ado, I'll turn it over to Philip.
All right. Share screen. Perfect. Now, excellent. All right. Well, thanks for the introduction. Yeah, like I said, I'm Philip Reger. I'm a PhD candidate, third-year PhD candidate at the University of Western Ontario in the Department of Earth Sciences, and also a member of the Institute for Earth and Space Exploration. My research focuses on meteorites, which is what I will be spending the first couple of minutes talking about. And I think one of the bigger questions, first of all, is what are meteorites? So meteorites are basically space rocks that landed on Earth. If they're still floating around in space, we call them meteoroids. And basically, as soon as they enter the atmosphere, they start to burn up, and we will call them a meteor. So basically, all your shooting stars that you can see, on summer nights, are space rocks that burn up in our atmosphere. Some of them make it to the ground, so they become meteorites. But if not, they just burn up, and that is the majority. The majority of dust and small rocks that ever enter our atmosphere, they burn up before ever reaching the surface. So where do these meteorites come from? The vast majority of meteorites come from asteroids in the asteroid belt, or asteroids that are that orbit closer to the Earth. We know that there's at least about 150 meteorites from Mars and about 250 from the Moon. And there are a couple of meteorites where some people think they might come from comets, but that's not confirmed yet. But in theory, it should definitely be possible that we could get meteorites from comets. So how do they get here? Through collisions, through two asteroids, for example, colliding, or an asteroid colliding with the Moon and ejecting rocks from the Moon. And if the impact is fast enough, strong enough, the rocks will leave the gravity field of the asteroid or the Moon or Mars, and after a couple of maybe million years, eventually might find itself crossing Earth's orbit and land on the surface of the Earth. And there's basically three types of meteorites. Basically, in a nutshell, we have iron meteorites that come from the cores of planetary bodies. So from asteroids that maybe form the core, like Earth has a core, Mars has a core, most planets have a core. So these iron meteorites come from there. Stony iron meteorites are a bit more of a mix. They have they might have remelted before they got ejected and ended up on Earth. And then we have fairly basic stony meteorites, which can come from the surface of the Moon, the surface of Mars. They can come from asteroids that never underwent any melting. So why are these meteorites important is they are very important because they are the only accessible samples that we have from asteroids, at least for now. They are the leftovers of the very first stages of the formation of our solar system. So our solar system formed through the collapse of what we call a molecular cloud that formed the sun very early, and it's a disk of gas and dust formed around the sun that was spinning, and these dust grains stuck slowly stick together, coagulate, and they just grow and grow and grow until they become pebble-sized, and eventually they're a few meters in size, and they will become what we call planetesimals, small planets. And these planetesimals collide with each other or with other planets, and through these collisions, more and more material gets accreted onto a planetary body. Basically, that's how planets grow. And meteorites are, like I said, leftovers from that process, basically, and can provide us as very, very important clues that we otherwise wouldn't be able to access. And just a few examples about that is what the chemistry of meteorites. I focus on the chemistry of meteorites, what they can tell us about the early solar system is. So it's because of meteorites that we know that the solar system is more than 4.5 billion years old. We assume that most of the meteorites we have were the building blocks that made up all the planets in our solar system. So if we understand how these meteorites formed, we might have an idea of how the planets formed and what they are made of. At the same time, they can give us an idea of how long did it take to form planets. If we know how old the meteorites are, we might be able to know how long it took for Earth to grow to its current size, or if we know, maybe just to half its size. And so the current thinking is that Mars, for example, grew to its current size in 3 million years, basically, whereas Earth probably within 10 million years, and then over the last, let's say, or the next 50 to 100 million years, grew ever so slightly to its final mass now. But of course, Earth and Mars were still growing. We still have dust and rocks and material from space that constantly fall onto our planet. So technically, it's still growing. And one other thing that meteorites can tell us is they can tell us how did Earth or Mars and some asteroids look like when they formed. And the answer there is that the whole surface was molten. So the whole planet was covered in lava and magma, basically. So what I do with the meteorites is that I basically destroy them, which is always hurts a little bit, but I cut them into pieces, I crush them into powder, and I dissolve them in acid, so that I can separate the chemical elements, so I can look at, say, magnesium or lead. Those are the two that I'm mostly looking at. And then I analyze them using expensive lab equipment. And I do all of this in a clean room, which is why you see me wearing a hairnet and a coverall bodysuit, basically, just to make sure that no dirt, no contamination from the outside gets into the lab. So yeah, that's basically what I do, what I work on. Next, I'll talk about the Junior Astronauts program, which I believe is about a year old now, because it was last year that Canada announced that they will be part of the return to the moon led by NASA. They will be part of the Lunar Gateway, which is basically an international space station that won't be orbiting Earth, but orbiting the moon. And Canada has basically promised to be a part of that. So the Junior Astronauts program wants to inspire the next generation of astronauts, space scientists. And if we can go here, so with the objectives here, we can say we want to get youth excited. We can, we want to show them what kind of careers you can go in and still be part of space. You don't just have to become an astronaut. You don't just have to, study geology and then, focus on meteorites. You can be an engineer. You can be a doctor. You can be a biologist. You can do pretty much almost anything has its applications in some form to the space industry. Even if you're a communications grad at the end, you can still work for CSA, for NASA, or for SpaceX, for all these companies that work to make space more, or so that we can keep going in space. So the Junior Astronauts program is basically 3 streams with activities, and of which all are important in when you go to space, and or just going to space or learning about space. And these 3 streams are science and technology, fitness and nutrition, and teamwork and communication. And what we can do, and you can see some of these activities, like they can be physical in nature, they can be like I said, teamwork, team building exercises, or anything science-based like coding, programming, and a lot of math goes into flying to the moon as well. So what you can do as an educator is, if you do one such activity with your class, you can enter a draw for an astronaut or a space expert to visit your school. And I think the deadline is coming up at the end of this this month, February, to enter that draw. And yeah, those are very exciting activities. And how great would it be if you were to meet an actual real live astronaut? And for the kids, for the youth, we have, if you complete one activity of each of those 3 streams that I mentioned, you can enter a draw to participate in a week-long, all expenses paid camp at the CSA, the Canadian Space Agency headquarters, and where you get to work with astronauts and space scientists and engineers. So that's a really cool thing as well. And I think that deadline is at the end of March. I will provide, I'll show the link, I think, in one of the next slides. This is a picture of that camp, I think, from last year. And yeah, so here we have the link to the Junior Astronauts program. You can, if you follow the yellow arrow, you can register, and you can basically find all the information that is needed to participate right over there. I'm sure that link will be provided down the line. So yeah, this is just a reminder of the dates. End of February is the draw for astronaut visits is the deadline, and for students it is at the end of March. And then the camp at CSA headquarters will be in July or in August. So yeah, so today's activity will be the patch maker. I'll get into that in just a bit. First, just a reminder as well that in almost all STEM disciplines, science, technology disciplines, women and girls are still very underrepresented in those fields. And again, in terms of space, as I said before, you don't have to be an astronomer or a geologist. You can do so many different things and still get into space. And I just really want to encourage everybody, and especially girls, to do that, or to think about it at least. So yeah, so the patch maker activity.
Oh, sorry, Philip. I'm just going to jump in. Before we get to the patch maker, maybe we can get a couple of questions in.
Yeah, absolutely.
And then we can move along. We can leave up that slide. We may actually want to back up to some slides depending on some of the questions. You mentioned at one point that with the continued accumulation of dust and other particles from space, that the Earth continues to grow. Is that growth measurable? Do we have a rate that we can talk about?
There is a rate. It's in terms of the mass of Earth, it's not substantial at all, but I think, I'm not entirely sure, but I think the rate is something like basically a ton per day. So
a ton per day.
1,000 kilograms of material falls onto Earth each day, which again, if you consider that the Earth, I think, is Oh, it's an incredibly large number. A ton is nothing compared to that. But I believe it's in the magnitude. It's an order of magnitude of around a ton, basically.
Right, but a ton is still fairly considerable when you think about a full-size car coming
Yeah,
from space every day and landing on Earth.
yeah.
That's pretty interesting.
Most of that is dust, obviously, but like you won't ever. Nobody's ever died from a meteorite impact so
Well, I'm
far.
glad to hear that.
Yeah.
Um, Jamie M. from Michelle Shane Matten's class asked about alien life forms on meteorites. So maybe we can broaden that question to any kind of biological material. Is there life, is there biological material coming from space?
So far, no, but there have been at least two meteorites from Mars that were highly, very controversial, where studies were published with results where they claimed that some of the structures in the meteorites uh, could only have been formed through bacteria, but so far that hasn't been confirmed. Most people have basically said no, it can still be like those structures can still be formed through interaction with water, for example, which we know that Mars had in the past. But that's definitely an interesting topic, and there is this theory called panspermia, which says that life on Earth came through meteorites, most likely from Mars. But again, that's just a theory, and it certainly doesn't answer anything in terms of how life may have formed to begin with.
One other question from Ahmed in Tara Bridger's class, asking if you were referring to the Big Bang Theory when you talked about how the solar system formed.
No, so the Big Bang created the universe, the whole universe, about I think it's 13 billion years, 13 to 14 billion years ago. Our solar system is 4.5 billion years ago, so it's about a third of the age of the universe. So like this is not my area of expertise, but in a nutshell, stars form and eventually they run out of fuel and then they die, sometimes quite violently with supernovas, and this stardust and the stuff that explodes from these supernovas um, feeds basically other star forming regions. So our star is made up of material that was formed in past stars, and everything in our solar system is made up of material from past stars. So yeah, that's kind of the difference between, I guess, the Big Bang, which happened a lot earlier compared to the formation of the solar system, which is in that term more recent.
Okay, that's great. We have another interesting question, and I'm wondering, and the question is about the smell of meteorites. Do they have a smell?
Um, Not when you're holding them, or looking at them. Maybe, if you find a fresh one, it might still smell a little bit burnt because they come through the atmosphere, they burn up, they create this fusion crust around the rock, on the outside of the rock. So, maybe there's a bit of a burnt smell. But what I can say is that in the lab, once I add some acid to meteorite, then some of them can smell quite badly.
So that takes me to my one question that I had. You mentioned that largely when you're analyzing meteorites in the lab, you're looking for magnesium and lead. Why those particular elements?
So that is, if radiometric dating is a term, this gets quite complicated. Basically, you can measure the ages of meteorites or also rocks on Earth using lead isotope compositions. It's complicated. I think go too far for me to really explain this in detail. But if you look at lead, you can determine ages of rocks. And for magnesium, you can do basically a similar thing, but that is more limited to the very, very beginning of the solar system.
Excellent, thank you. So why don't we move along to the patch maker, and if there's more questions, we'll get to them after the next part of the presentation.
That sounds great. That sounds great. All right, yeah, so today's activity that maybe everybody in the classroom might be doing that now, or you already did it, or you might do it later on. So today's activity is patch maker, where you design your own astronaut and mission patches. So what these patches are is that each astronaut always has his own astronaut patch with his name, with the space agency that he's with, and with some image that is meaningful to that astronaut, to either his training, his development, or his interests, or where he's going, like is he going to the moon or not. So we have an example here from David Saint-Jacques, the most recent Canadian astronaut to be in space. He was up there, I think, on the ISS for, I think, almost 6 months this past in 2019. So he has here, you can see the Earth in the background with some stars that actually I think show more detail. Yeah, so we have stars beyond Earth, the North Star and the compass rose in the middle, which signifies basically exploration and navigation. And he chose 4 colors that signify innovation. I don't remember exactly which ones those are, what stands for what, but those were meaningful. This is meaningful symbols to him and his career, basically. And we have some other examples from Canadian astronauts, from all the past Canadian astronauts, where some of them have worked on the space shuttle, so that features prominently in some of those. Or if we go to the next slide, we have a nice example from Hadfield in 2001, where the Canadarm is very prominently displayed, because he was working a lot with that on his mission. And yeah, so these are, you can use these as inspiration. These are some really spectacular patches. And then we have some other examples from junior astronauts who have already done this activity. And as you can see, you can be as detailed as you want. You can, whatever mission you interests you, if you want to fly to Pluto, if you want to fly to the moons of Jupiter or the rings of Saturn, your imagination is basically the limit. And so that is the first part of the exercise. The second part is where you and your crew members design a mission patch. So every space mission, so an astronaut will have 2 patches. He'll have his own personal patch, and he will have a patch of the mission that he's part of. This one here is again an example from David Saint-Jacques' mission to the ISS, where he was assisted or joined by Kononenko, a Russian cosmonaut, as they call him there, and McLean from the United States, from NASA, as they spent time aboard the ISS, which I think was, I guess, the 58th mission to the ISS. So yeah, so you have all the crew member names, you have the mission number, and again, a meaningful image that is relevant to the mission that you are a part of. And again, yeah, so this is what they did here for Expedition 58 is they had the Earth below. The ISS, orbits Earth every 90 minutes. It's about 400 kilometers above us. And they have, again, a compass rose, which is a very popular theme. And they show the ISS, of course, as well, as basically their home for the period of their expedition. So yeah, so that is the second part of the activity, is to design your mission patch with your crew members, have all their names on it, find out a good mission number, mission name, and try to find a meaningful image for that. And I think with that, I'm done. If there's any more questions, I'm happy to answer them. Make sure to follow the CSA, the Canadian Space Association, on social media. And yeah, I think that's it for my part for now, unless there's any questions.
Fabulous. Thank you, Philip. If you can just click your stop share button on your screen.
Absolutely.
We'll go back to full video. We did have a couple of questions. One from Caden, wondering how much damage a meteorite can create on Earth, or perhaps has created on Earth.
So almost everybody, I assume, is going to be aware of the theory that the dinosaurs went extinct because of meteorite impact. So that's one example. So it can do a lot of damage. That was just to not scare anybody. Those impacts happen very, very, very rarely, like every 100 million years, maybe even every billion years. But in more recent terms, there's a meteor crater in Arizona, which is in a desert, so it's very well, it was preserved very well because there's not a lot of weathering. And it's basically a crater, 1 kilometer in diameter in the middle of the desert. And that, I think the impact happened, I think that was about 30,000 years ago. So there can be a lot of damage. There have been reports of meteorites crashing through roofs of houses. And I think there's even a story that a dog got hit by a meteorite once and died, which is very unfortunate. But as I said before, no humans have ever been killed, at least, by meteorite impacts. There have been some asteroids, meteoroids that entered the atmosphere and exploded there, as most recently in Russia in, I think, 2013, where the explosion, the shock wave, did cause some damage and some injuries. So, yeah, but in general, the risk isn't very high.
Thanks. One other question we had relates to your answer to the previous question. And it's about how one meteor was able to wipe out the dinosaurs. What was the impact of that actually had that effect?
So I don't remember exactly how big the impactor was. The crater can still be found in Mexico on the Yucatan Peninsula, and is, I believe, 100 kilometers across, basically. So it had to be a really sizable impactor. And what happens during impact, first of all, is that the rock, if it gets warm enough, vaporizes, becomes turns straight into like magma, basically lava. And you have, through the explosion and everything, you have so much dust that gets thrown into the atmosphere that what happened was what they call a nuclear winter, or a nuclear summer, was that there were no sunlight was able to make it to the surface of the Earth, which caused basically all the plants to die out. It poisoned all the dust material that fell into the oceans, poisoned the water there, so that all or most of the animals in the oceans perished as well. So the impactor itself didn't wipe out the dinosaurs in that sense. It was more the consequences of this impact that made it very difficult for, I think it was 99% of life forms, or 95% of all life forms died out within the aftermath of that impact.
All right. So one last question before we go. I always like to ask this. You mentioned earlier you don't need to be a geologist or an engineer or what have you to be part of Canadian Space Agency. Maybe you can tell our classrooms a little bit about your educational journey, where the stops that you made along the way to get to this point.
Yeah, I'd be happy to. I'd say my journey was not a very straightforward one. I certainly didn't. I mean, I was always interested in space as a kid, as a teenager, but I never really considered studying to become a space scientist or anything like that. It was just happenstance in a way, and I think I do hope that what I'm about to say kind of also tells you that you don't need to have it figured out right away. You can take detours along your way, and if you really want to go into space, you will find a way to work in space science or planetary science. So what I did, I started out in civil engineering at very first, but then dropped out fairly quickly because I didn't enjoy it as much. My favorite class was actually geology. So I went into geology on that program. This was back in Switzerland, where I grew up in, and doing geology, there were a few classes that were related to space and planetary sciences, and those kind of interested me the most. And also, those were the classes I was best in. So for my master's, I decided to specialize a bit more into that region, and did my master's thesis on iron meteorites, and now I'm here working on meteorites at Western University.
Fabulous. Thank you so much. It's always really nice to hear the stories that seldom is the path a straight line when you find yourself in a career. So find something that you're interested in, and you'll find a way to turn it into something that can become a career.
That's the most important thing anyway, is be passionate about what you do, and everything else will be, I mean, I think especially for the next generation, they have so many opportunities coming up with technology that anything, for space in particular, but just in general, you'll be able to do anything that you want.
Fabulous. Thank you so much. Thank you, Philip, for all your time today.
You're very welcome. It was a pleasure.
For the classrooms watching, I'll just let you know that we have a busy week on live event next week. We have 2 junior astronaut live events on February 11th at 1 o'clock. Magdalena Weiris from the Canadian Space Agency is going to join us. Magdalena is a project engineer on the RadarSat constellation mission and the deputy lead for the Junior Astronauts Campaign. On February 12th at 11 a.m., Elisa Dong, who is a peer of Philip's, will be joining us to discuss earthquakes and Martian seismic data that she's using to better understand the Martian interior. Also, live event next week, not related to Junior Astronaut, on February 10th, we will be doing a session on synthetic biology with a group from the University of Toronto. So registration information for each of those 3 sessions will be coming out in the next day or 2, and look forward to seeing classrooms back with us next week. Thank you very much. Enjoy the rest of your day. Take care. Bye-bye.